Hello everybody, my name is Tariq Mudawi and thank you for attending my final presentation for my defense. I would like first to thank my chair, Dr. Wang, and my committee members, Dr. Polai and Dr. Liu. And I will start by stating the agenda for this presentation. First, I'll go through the introduction, followed by the literature review, and then the challenges for this research and the artifact design and description, followed by the solution demonstration, and then I will show the testing and evaluation and results for our solution, and I will state the limitations for the solution and future research, and wrap up with the conclusion. And then finally I will get the questions for anyone who might have any question. The IoT environment is expanding rapidly. We are expecting around 25 billion IoT devices by the year 2021, according to Gartner. The home IoT security is very risky when compared to other sectors of IoT like healthcare and industrial and corporate. There is insufficient security in the smart home environment specifically, which one of the major items that drives this research. So we needed research in this area to address this issue of security. This is a typical smart home environment equipped with different IoT devices, things like tablets, smartphones, routers, PCs, laptops, smart appliances, and smart plugs, smart ovens, and many more. The motivations that drive this research, it's a new area of research, so it's very interesting to get into. And there is limited research done in the area in general, so we need to do more research to establish better security for the home environment. And the need for standard solution also is a big motivation, because most of the solutions address just one device or subset of devices. There is no many solutions that address the whole in-home smart home environment. And plus, finally, I have personal interest in the subject, obviously. The research questions that drive this research, we have three main research questions. Number one, how to develop and implement an anomaly-based intrusion detection system in a smart home environment that is accurate, efficient, and easy to operate by an average homeowner. Question number two, how to establish a device management method in the smart home environment that can easily validate an IoT device is a legitimate device added by the homeowner to the home network. And the final question, number three, how to protect a user's privacy from being revealed by IoT devices that use plain text format to exchange information. Those are the main three research questions that we used to establish our research. And our purpose statement for this research is to create a standard solution for securing the smart home environment that can work with heterogeneous IoT devices sourced from different manufacturers and easily used by a homeowner. The methodology we followed in this research is design research science, and that is because we have an artifact, an instantiation in this case, and we followed Beffer's ETAL 2008, which it requires 7 principles to follow in order for the research to qualify as a design research science, and we followed all of them. The literature reviewed, for the literature review, we reviewed more than 100 papers targeting the smart home security, and we identified 5 major gaps in the literature that we used to drive this research. And here's 5 gaps. Number one, there is limited research in the area of smart home security in general, so the research is needed to establish better security. And number two, solutions are mostly specific, meaning there is no standard solutions that cover the smart home environment as a whole. There is only few of them that we still need this. So most of the solution targets devices, specific devices, like the paper introduced by Leo Hu and Zamaya here is targeting smart meters. Number three, some of the solutions or most of them are theoretical solutions, assuming things like public key infrastructure algorithms to protect the smart home environment or the home environment specifically, which we know is not valid in reality, because smart home environment specifically do not come out of the box with public and private key installed on them by default. So those solutions are mostly theoretical. We need a real world solution that applicable to home or to smart homes. And number four, some solutions are complicated or expensive, like the one that presented by a company called Bitdefender. They have a product that cost $199 per person, and which we need actually the solution to be affordable and at the same time efficient and accurate. And the last gap, most of the solutions that we found, most of the standard solutions that we found are not accurate, as we will see when we compare our solution to the other solutions. The challenges we have in this research is to create a simple yet efficient intrusion detection and prevention system to protect the smart home network, and that system should run 24/7, monitoring the home environment without the user intervention, and it should detect old and new attacks. It should also have a simple and easy to use user interface that the user can use, and it should be efficient without noticeable effect on the network performance. And finally, it should integrate seamlessly with other IoT HAS engines, because we have other two engines, as we will see shortly. Challenge number two is to protect the home owner private information leaking in clear text. And the final challenge is to manage the IoT devices in the home network. This part we describe the artifact design and we describe the artifact design and description. Our solution is named IoT HAS, which stands for Internet of Things Home Advanced Security System. And this system is a comprehensive solution to secure home IoT devices, and it aims to overcome the shortcomings of other home IoT security solutions that we've found in the literature review. And the IoT has composed of three main engines. The first one is an intrusion detection and prevention engine. The second one is a device management engine, and the third one is a privacy monitoring engine. This is an architecture of the design of the IoT HAS, and we can see the three engines inside. The first one on the left is the intrusion detection and prevention engine, which work 24/7, as we mentioned, protecting the home environment, detecting if the packet is an attack or no, and then block the package or detect or alert the user. The middle engine is a device management engine, where it scans all the devices and displays them to the user via the user interface, and the user can decide whether the device is good or legitimate or no, and he can disconnect or block the device. And the last engine is a privacy monitoring engine on the left, and this is where IoT HAS will inspect the packets for clear text information, and if so, it will alert the user, and the user has to take an action. The engines, we will describe the engines in details here. The intrusion detection engine and intrusion detection and prevention engine is an anomaly based intrusion prevention or intrusion detection engine. It runs in two different modes of operation. it either in line with the traffic, meaning it sits in line with the traffic. This is an inline mode, or it can be installed not in line with the traffic, which we call it here running as a passive mode. The solution is based on a machine learning algorithm, and the intrusion detection prevention engine is composed further with 4 modules. The first module is the traffic filtering module, which can filter the traffic by TCP or UDP, or by protocol type like TCP or UDP, or class of service such as HTTP or Telnet, or it can filter by source or destination port or IP. And the second module is the feature selection module, which selects the important features from the packets that are used to determine or to predict if the packet is an attack or normal. And the third module is analysis and detection module, which actually use the feature extracted to do the detection of the packet. And the last module is the alert and prevention module, which prevent or block the packets, or it can alert if running in a passive mode. This is the architecture of the intrusion and detection engine, composed of the four modules that we just described. The first one on the left, upper left, is the traffic filtering module, where it filters the traffic by either a class of service or other classification. And the one in the bottom left is the feature selection module, where it selects the important feature from the packet, and then it forwards the packet to the analysis and detection module on the right bottom, where it detects if the packet is an attack or normal. If it is an attack, it will make a call to the alert and prevention module on the top right. And if it is a packet, if the packet is good, it will allow it to go to the home network. The privacy monitoring engine is to determine the unencrypted packet using a method called Shannon entropy test, which is a method that determines if the string is encrypted or no, based on a threshold value. If the number of characters in the strings is less than that threshold value, it will regard it as a clear text. Otherwise, if the value is over the threshold, it will regard it as encrypted. So the privacy monitoring engine inspects the packet load for unencrypted text, and if found, it alerts the user and advise him to disconnect the device. The device management engine scans the home network for new devices, and it gathers information like IP address, MAC address, and device vendor if found, and assume all devices are valid if it's running in the passive mode, or block them by default if run in inline mode, in line with the traffic meaning. The homeowner confirms the new devices and block or disconnect the suspicious device from the user interface. So actually what happened is IoT has runs, and then device management runs and gather all the devices in a database table, and then when the user views a GUI, the information of those devices will be displayed from that database table on the backend to the user in the GUI, and the user can determine which device is valid or not valid and disconnect or block accordingly. This is a picture of the incoming traffic, and we can see the traffic is coming from the internet, going to the intrusion detection engine, and we can see the 4 modules inside the intrusion detection engine that we described before: the traffic filtering, feature selection, analysis and detection, and alert and prevention. And then from there it goes to the device management, where devices are scanned and the user can view them in the GUI and decide whether the device is valid or no. If it is valid, it will be allowed to go to the connect to the network. Otherwise, the user can disconnect either by blocking it or by physically disconnecting the device. And this is a figure of the outgoing traffic, which is the reverse of the incoming. And here we can see the packets are coming out of the home IoT device, and it will be inspected by the privacy monitoring engine for plain text. And if found, the user will be alerted through the GUI interface. Otherwise, the packet will go to be inspected further with the intrusion detection engine, and it will be either blocked or the user will be alerted according to the mode of the operation, whether inline or passive mode for the intrusion detection engine. This part will demonstrate our solution. By demonstration, we mean we will show the tools and method we use to operate our solutions. Since our solution is based on machine learning, we will need a data set to train the model. And we chose to go with the Canadian Institute of Cybersecurity for Intrusion Detection System 2017 dataset, which is one of the best datasets available now. It has many attacks types, attacks like DOS, DDoS, brute force, web attacks, and many more. And since that database is very huge, it has over 2.8 million records, we decided to go with a sample of that database set. When we called it CIC IDS 2017 sample, and that sample represents 5.34% of the original dataset, and it has this number of attacks which shown in table 1. We also need another tool, which is a machine learning algorithm, obviously, to run our models. And the way we selected the machine learning algorithm is we chose 7 machine learning algorithms, and then we compare them to select the best. And we selected the logistic regression, support vector machine, kernel SVM, naive Bayes, k-nearest neighbors, decision trees, and random forest. And thus we we trained each of those models using the CIC IDS 2017 sample dataset. And here table 2 shows the result of the comparison. This is the confusion matrices for all the models, and we can see that decision trees has the best performance when compared to all the models together. And also from these confusion matrices, we calculated the statistics like accuracy, precision, recall, and F measure. And again, we see decision trees has very good performance, and we like that, even though random forest is slightly better, but we suspected that it might have more attached to the data. I think it is very attached to the data. Overfitting. It might have overfitting issue, and that's why we went with decision trees. Here, this is we did also dimensionality reduction to further enhance our model, and we did in the dimensionality reduction via feature selection, which selects the best feature, because originally the dataset, the CIC IDS 2017 sample dataset has close to 80 features. So we decided to do feature selection, and we selected the best 5 features, which will make our model very efficient and fast and lightweight, which a feature needed for IoT devices since they are resource constrained. This part, we test and evaluate our solution, and we did that through 4 different ways. The first way of testing and evaluation is to compare it against similar solutions, and we compared it to 4 solutions that are also developed to protect the home environment, and they are based on the same CIC IDS 2017 dataset. So the comparison would be fair in this sense. And table 5 here shows comparison. We actually ran all the models, and then we extracted we calculated the confusion matrices, and IoT is showing the best performance here when comparing the true positive, true negative, false positive, false negative. And also we compare the statistics of accuracy, precision, recall, and F measure. And IoT has also overperformed the other model, as we see in table 6. Table 7 here, we also compared the CPU time for both the training and testing time, and again we see IoT has the less time among all, so it is much faster. The time here is shown in seconds. The second way of evaluation, we did simulation test. We actually tested IoT has in inline mode inside virtual environment, and we did simulation test in that setup. And inline mode, here we used 3 virtual machines. The first one is an Ubuntu router machine, Ubuntu 18.04, where we installed IoT has on that router machine. And then we have the home victim installed in Ubuntu 18.04 also. It represents the victim machine, and the attacker is sitting in the third machine, where we installed Kali Linux equipped with attack software. And we can see here we have 2 network, the 232 for the attacker and the 248 for the victim. So IoT has a setting in line with the traffic, routing it from the attacker to the victim. The first set of attacks, we use a tool called LOIC, which stands for Low Orbit Ion Cannon, to send DDoS attacks from Kali to the home victim. And we ran 5 rounds of attacks, and each rounds we captured the attacks in a log file. We calculated the number of packets identified as attacks. Again, is the total number of packets for each round, because all the packets originally should be attacks since they are coming from an attack tool. And that way we can find out how many of them are identified by IoT has as an attacks. And here is the percentage of each packet in each round identified as attacks. We can see it range from 90% to 99%, with an average among the 5 rounds of 97.623, which is a very good detection accuracy for DDoS attacks. The second test, we tested the brute force attacks. Again, we ran 5 rounds of test. We used a tool called Medusa that comes with Kali Linux. We can see here the highlighted command in yellow. And similarly, we ran 5 rounds of attack, captured each round in a log file, and we found the percentage of percentage of packets identified as attacks in each round. And we can see it has very good accuracy, ranging from 93 to 99%, with an average accuracy of 98.484%. And for the last test, we used the cross-site scripting simulation test, and we used a tool called XSSER to simulate the attacks from Kali to, again, is the home router, again is the home victim, sorry. And here we can see on the left the command for sending the attacks, and on the right here in this cross-site scripting, we don't need to capture the attacks in log files, and that is because the tool itself will tell you if the attack is successful or no. And here, as we see in figure 10, it shows successful 0 and failed 558. I guess this is the number of packets sent, and it means that IoT has prevented the attack successfully. The third way of testing, is to test IoT has in a passive mode inside a virtual machine, and we use the same three machines like before. Only here they're sitting in the same network. So if you notice here, the network is 248 in both sides. So IoT has is not in line with the traffic. So again, we used Loic to send the DDoS attack, and we used 5 rounds similar to the previous situation, and we calculated the percentage of packets identified as attacks in each round, and then we found the average detection accuracy among the 5 rounds, and it shows 98.832%, which is a very good detection for DDoS attacks. And we also used Medusa to simulate brute force attacks, and we used 5 rounds, each one captured in a log file like before, and we calculated the percentage for each round for the packets identified as attacks, and then we calculated the average percentage among the 5 rounds, which shows here 96.045%, which is a very good detection accuracy for brute force attacks. For cross-site scripting, we again used the XSSER tool, and we send attacks against the home victim, and as we see here in figure 13 on the right, the attack is not successful because successful is showing 0 and failed is 558. The fourth and final way of evaluating and testing our solution is we tested IoT HAS in passive mode on a Raspberry Pi 4 this time. So this is outside of the virtual environment, and this also proves that IoT HAS can run in a resource constrained device similar to an embedded device, which is a Raspberry Pi. And this setup here, we installed IoT HAS into a Raspberry Pi 4, and we installed Kali Linux into a Raspberry Pi 3B plus, model 3B plus, and we send attacks from the Kali Linux against a wireless Canon printer. So these IPs are the actual IPs in the home network, the real IP addresses. And first we started with the DDoS attacks using the same tool, Loic, and we established 5 rounds of attacks similar to previous situation, and we found the percentage of attacks, percentage of packets identified as attacks in each round, and we finally calculated the average percentage of attack among the 5 rounds, which found to be 98.619%, which is a very good detection for accuracy for DDoS attacks. And we also simulated the brute force attacks. This time we used a tool called Hydra, which is one of the best tools for simulating brute force attacks. And we calculated 5. We ran 5 rounds of attacks for brute force, and each round we, like before, we calculated the percentage of packets identified as attacks, and then we found the average among the 5 rounds, which shows 97.337, which is very good detection accuracy for brute force attacks. And actually for the brute force attacks here, we run the attacks against the home router. As we see here, it's 192.168.1.1. This is a typical IP address for home routers. And also, when we run the cross-site scripting attacks, we run it against the home router, and using the XSSER tool. And the results came in figure 17 on the right here. It shows that the attack is not successful because successful is 0 and failed 1. So IoT HAS is able to prevent the cross-site scripting in the Raspberry Pi environment successfully. We also tested the device management in the 2 modes of operation. In the inline mode, the way we tested it, actually we ran IoT HAS, and that will entitle the device management to run, and the IoT HAS will capture all the devices into a backend table, the device IP and MAC address and device vendor if found. And then when the user opens the GUI interface, the one that shows here in figure 18, he will see the devices real time, and in inline mode all the devices will be blocked by default, so the user can verify and then unblock the device here by putting the IP address and unblock it. So initially scan automatically block devices. Homeowner can block or unblock devices from the GUI, as we just see here. We also tested the device management in the passive mode inside virtual environment, and we can see here that in this scenario the user has to verify legitimate devices via the GUI, and then the user must physically disconnect the suspicious device because there is no way to block the device in the passive mode. The limitation for this research, we have few limitations. Number one, we tested in a virtual environment, and that is because the virtual environment allows us to set up two networks, because the actual home environment has only one network, so we needed two networks, especially when we run the test for the inline mode, where the attacker has to be in a different network than the victim. The other limitation is that the Raspberry Pi has limited resources and capabilities when compared to a real router, and that affects the performance of IoT HAS. And the third limitation is with the device management. In this version, it has limited functionality of scanning and displaying the devices. So it does not authenticate the devices by default. The user has to take an action by disconnecting or blocking the device. The privacy monitoring engine also has limitation because it only monitors plain text, not the personal identifiable information, and the user has to take an action when he gets an alert to disconnect the device. Also, the IoT HAS in this version, we have to keep training it every few months maybe, because as it gets old, it will produce more false positives, and this is another limitation. For future research, we concentrate on addressing the limitation of this research. And we are planning to promote for the device management. We are planning to promote it to identity and access management, and that will allow it to authenticate devices without the user intervention. For the privacy monitoring engine, we plan to promote it to a real privacy protection engine, where it can do a deep packet inspection to detect user PII. And then it will alert and block PII leakage by default. We also plan to make IoT HAS self-trainable through deep learning algorithms such as artificial neural network, and that will allow IoT HAS to learn new attacks from new data. And that way we can exclude manual training. To wrap up this, in conclusion, we are filling the gap of a limited research area. We are building a foundation for future research. We introduce a standard solution for heterogeneous IoT, home IoT devices. The solution is light yet efficient, and it also targeting non-technical homeowner. The uniqueness of our solution falls in that it is a standard solution, and it has a custom IDS IPS system for smart home, and it has a device management simple operation that allows the user to exclude invalid devices, and it has also a privacy monitoring engine that monitor clear text and alert the user if any. And the user interface of this application also make it very easy for the user to get alert for privacy issues or disconnect devices or block devices, or also get information about when was the last threats detected on the system. And that end our presentation. This is the references. Please question and answer if you have any. Thank you very much.